Welcome all. We'll start today Raman spectroscopy. So now spectroscopy. This is discovered by Indian scientist, that is Chandrasekhar Raman, and here we used laser is used, and here we talk about of scattering. And if I this is the phenomena, let's say here my molecules is there. This is molecules, and we are giving any electromagnetic radiations to it. Electromagnetic radiations, and it have the energy of h nu, and this h nu, or we can say the photons. So whenever you give this electromagnetic radiation to these molecules, then there is a two chances it will happen that after the collisions we are colliding electromagnetic radiations with molecules. So after the collisions, so we are doing collisions between electromagnetic radiations that is having a photons or the h nu, this amount of energy, or you can say this amount of that is a photons having energy h nu. So we are doing collisions between electromagnetic radiations and molecules. So after these collisions, there is a two chances it can happen that after these collisions there can be the exchange of energy between the electromagnetic radiations and the molecules. After we are doing the colliding these electromagnetic radiations having h nu frequency with molecules, there can be a two chances, either the there can be a exchange between these molecules and the electromagnetic radiations, or there can be no exchange between these molecules and electromagnetic radiations. It means that there can be a two chance that after collisions between electromagnetic radiation and the molecules, they simply they reflect the they release the energy with same frequency, that whatever you give this h nu frequency, after collision also the same amount of frequency is released. Let's say that h nu. Okay, this is the first case, and so I can write here that case is no exchange of energy. No exchange of energy, or frequency is not exchanged, means whatever you give this frequency, the same amount of frequency has released. This h nu, you say that E equal to h nu. So if I say that energy, or I can say this is the h, means this is the Planck constant, and this is the frequency. So I can simply say energy, or I can say the frequency. So I guess I will say that this amount of energy or frequency I give it to these molecules. After giving these molecules, there will be collisions between whatever I give the energy or the frequency and the molecules. There will be collisions. After the collisions, either it will either the collisions give results in a exchange of energy between this between these radiations and my molecules, or other case is that there will be no any exchange between the molecules and the energy or radiations. So first is no exchange of energy between the molecules and the radiations, and the second case is exchange of energy has happened between these molecules and the electromagnetic radiations. So whenever the exchange of energy is happened, or whenever the no exchange of energy, means this you will say in Raman spectroscopy, or that we will say that elastic collisions. And whenever the exchange of energies happen, that we will say that inelastic collisions. Okay, so after collisions, if the exchange of energy is happening, then that is called inelastic collisions, and if there is no exchange of happening after the collisions, that are called the elastic collisions. Okay, so here no exchange of energies happened. Whatever you give this h nu, the same frequency is released. It means this is the elastic collisions. Another case is that inelastic collisions. On inelastic collisions, there are the two chances that whenever whenever they are colliding, after collisions the exchange of energy is happening. It means the past case, exchange of energy between the molecules and the radiation. It means either the frequency whatever released, that may be the high frequency compared to the incident frequency, or that can be the low frequency compared to the incident frequency. It means that these molecules, after collisions, exchange of energy is happening. It means one case the exchange means these molecules, let's say the frequency is released with high frequency after exchange of energy, and other case the molecules released with low frequency after the collisions. So two things we will get for inelastic collisions. One is with, and also I can say frequency released with low frequency, and other case this A, and other case frequency released with high frequency, frequency released with high. So here that high frequency is released after the collision, here the low frequency is released. Okay, and this, and let's say if that if I have the 1000 molecules, and I'm giving to this 1000 molecules I'm giving the electromagnetic radiations, then it is found that experimentally that 900 molecules will do the elastic collisions. Means there will be no exchange of energy between this my molecules, that I have the 100 molecules, with whatever giving the electromagnetic radiations. Means 90 molecules, 900 molecules from 1000 molecules will go without no exchange of energy. Means this case will be happen in a maximum cases. Okay, means maximum molecules will do no exchange of energy, and we can say that 100 molecules can do the this inelastic collision. Means there will be exchange of energy has happened, and that case either it may be released with low frequency or it may be released with high frequency. So these things, if I draw graphically, let's say if I say here in this ground states, this is ground states. If I have that 1000 molecules and I am giving the electromagnetic radiations to it, let's say this h nu, and it have that excited states, this ones, and the chances is that this will be go here, let's say, and this will be, let's say, or I can say, means I these molecules gain this amount of energy and go to this high levels, and after that they released, means this is the gain of energy is h nu, here h nu, and released the same amount of energy h nu. It means there will be no exchange of energy happened. Means whatever electromagnetic radiations we have given, that it gains and it go to here, and the same amount of energy it has released. Means here no exchange of energy has happened. So this is the elastic collisions. This is the elastic collisions. Okay, where no exchange of energy happened. I can write no exchange of energy. no exchange of energy. And other case I can, and this second case where inelastic collisions, how can I draw this picture? Let's say these are the ground states. I have molecules 1000 molecules, and we are giving the electromagnetic radiations to it, h nu, and let's say it has that excited states like this. So it will absorb this energy, means this gain energies, and it may release. So we say that this is the for inelastic collisions. Inelastic collisions. So in elastic collisions, there are the two chances: frequency released with low frequency, another is frequency released with high frequency. Sorry. So elastic collisions, let's say frequency released or energy released with low frequency. Let's say this amount of, after gaining h nu, this was excited to, this molecule is excited to this energy levels, and it released this energy levels, or I can say this. So here h nu I have given, but it is released frequency is this. So here we see that whatever we given, that's h nu is greater than h nu dash. It means the frequency released with low frequency. This is the released frequency. This is the gain frequency. So this is the released with low frequency. Okay, because this is lower. Let's say this amount of this amount. This we say that, let's say this to this, and here this to this. It means that this is lower and this is higher. So I say that h nu is greater than h nu dash, means this is released with low frequency. And let's say this energy gaps is, let's say this is, we can say that delta E. Then I can write this one as h nu equal to h nu dash plus delta E. Means after adding this h nu with this is going to become h nu. Okay, so this is the inelastic collisions with low frequency. Okay, this is, let's say this is the A case, and other picture with high frequency that we can draw. This is also inelastic collisions. So this is frequency with high. This picture I can draw. Let's say our molecules is here in the ground states. So let's say for this, what happened that we are giving the electromagnetic, this is the ground states, and we are giving the electromagnetic radiations, let's say to this excited states. The molecules here is there, and low amount of molecules in excited also there. Okay, so if we give the electromagnetic radiations to this excited state, this is the excited states, then this will be given to this, and after release it will be released to this ground states. So from here we see this is that h nu you have given, nu you have given, after that it release that h nu dash. So here we see that this h nu is lower than h nu dash, and let's say this energy gap is delta E. Then we can say that h nu plus delta E is equal to h nu dash. Okay, so these are the three cases that is possible in after the collisions. Either it can be the elastic collisions, there we can draw the pictures like this, and other cases it can be inelastic collisions, for either it can be frequency released with low frequency, or it may frequency released with high frequency, that is inelastic collisions. The pictures we can draw like this. Okay, so if this picture, if I draw in a spectrum, then how we will get this peaks intensity? So you see that for where that elastic collisions, where that no exchange of energy is happening, this we will call that relay lines. So this we will say relay lines. And the frequency with frequency reduced with low frequency, this we will call that Stokes lines. They are called the Stokes lines. And this we will call that frequency with high frequency, this we call that anti-Stokes lines. Anti-Stokes lines. These are the relay lines. Okay, so if I draw this spot picture, then this is relay lines. So here this is the low frequency and this is the high frequency. So low frequencies are anti-Stokes lines. The intensity can be like this. We'll discuss more on it in after discussing it. So these are the high frequency lines. So these low frequency lines are we are calling, these are the Stokes lines. They are the Stokes lines, and these are the anti-Stokes lines. Anti-Stokes lines. Okay. So we will discuss it by whenever after studying rotational Raman spectroscopy and vibrational Raman spectroscopy. And one more thing, this is the relay lines. So the energy difference between this relay lines and this Stokes lines, anti-Stokes lines, or this Stokes lines, this is called Raman shift. And this is the characteristics of a molecules, and it will not change. It will remain constant if whatever the lines, whatever the Stokes lines. So these are the characteristics of the molecules. So we will discuss about of that rotational Raman spectroscopy, and there we will discuss again this Stokes line and anti-Stokes lines. So let's start with rotational Raman spectroscopy. So in previous class we have discussed details about of the rotational spectroscopy. So let's give a quick recap. So if I say about of the rotational spectroscopy, let's say rotational spectroscopy. So what you know this rotational spectroscopy? Let's discuss what are the needed for rotational Raman spectroscopy. That will quickly recap. So in this Raman spectroscopy, we need that concept of that energy gaps. So in rotational spectroscopy, you see that these are the energy levels. Let's say this is J equal to 0, this is J equal to 1. Let's say this is J equal to 2, and let's say this is J equal to 3. Then let's say that energy, this is given by B J J plus 1, where B is equal to H upon 8 pi square IC J and J plus 1. And we know that this is H is Planck constants, and this is the constant 8 pi square, and IC is moment of inertia, and this I is equal to m1 m2 upon m1 plus m2, and this is the speed of light. And this m1 m2, whatever the molecules, they are the masses, and this J is rotational quantum number. Rotational quantum number. Okay, so let's say if we giving this electromagnetic radiations to here, then what happened there, that here that selections rules for rotational spectroscopy is, that is delta J equal to plus minus 1 only this is the selection rules. So here whatever the energy will do, so from J equal to 1, here only we can do, here we can't do, because here J 1 minus J0 has to be either plus 1 or minus 1, or it can be happened from here to here or here to here, or also it can be the emissions also happen from here to here also, but here to here can't be possible. Okay, so that delta J is not equal to plus minus 2, not equal to plus minus 3. These kinds of uh, transitions we will not see, only this type of transitions we will see for rotational spectroscopy. So this is that energy for rotational spectroscopy. Okay, and for whenever we go, you will go for rotational Raman spectroscopy. Rotational Raman spectroscopy, what we see here, that let's say I am doing again this energy levels, this J equal to 0, this J equal to 1, J equal to 2, J equal to 3. Here the selections rule is delta J, that the selections rule is equal to plus minus 2. Unlike simply rotational spectroscopy where selection is plus minus 1, here that delta J is plus minus 2 and other one is 0. Okay, and whenever this delta J equal to plus 2, that is we will talk about of Stokes lines, and Stokes lines, and whenever this delta J is equal to minus 2, we will talk about of that anti-Stokes lines, and whenever this delta J equal to 0, this we will talk about of that relay lines. Okay, so here the transitions will be from J equal to 0 to J equal to 2, or can be this to this type of transitions we will see where delta J equal to plus minus 2. Actually what we see here, that let's say J equal to here, and that this is this, and this energy difference, this is the delta E. Okay, and this, so here we will see that here that E, let's say J 0 to 2. Okay, so if I talk about of that energy gap, that says that energy, so for rotational spectroscopy you will see that energy gaps, and if you talk about of the energy gap, okay, so energy gaps, for general energy gap what we see, that for rotational spectroscopy also we have discussed that delta E is, let's say general case I am talking about of general, so that is we can say that for rotational, we say for rotational we have discussed that is here that selection rule is plus minus 1. So here we see that E J plus 1 minus EJ, that is for uh, simply for rotational, but for this rotational Raman, that delta J is equal to plus minus 2. So here I will say that delta E is equal to, I can say E J plus 2 minus EJ, because here that's that energy gap, that selection rule is plus minus 2. Okay, so here if I talk about of that, we have discussed in rotational Raman spectroscopy. If you do this, then we will get that some value that we have discussed in the rotational spectroscopy. Now we are discussing about the rotational Raman spectroscopy. For this, let's say that E is equal to B J plus 1. So here J plus, in place of J I will put J plus 2, and in place of here for this case in place of j I will put j. Okay, so let's put the equations. So E is equal to B and j equal to j plus 2, so I will put j plus 2, and another is j, so in place of j I will put j plus 2, and this is plus 1, and minus again this value, that is bj j plus 1. Okay, so if I do this, after if I solve these equations, let's solve it b, and if I solve it jj, that is j square, or I can put first b j plus 2, and this is j plus 3, this is minus bj j plus 1, and if I do it, then this is j square plus bj, this is 2j, and this is plus 6, this is minus bj and j plus 1. So if I solve it, then I can say this is b, so let's multiply with b also, bj square plus bbj, and if I add it, 3j 2j, that is 5j, this is 3j 3j 2j, that is 5j, so 5j into b, so I can write 5bj plus 6 and minus b. If I here also, if I multiply bj, that is bj square, and this is the whole terms minus, so this is bj square, and this is again minus bj, because this bj and the minus, the again this minus, that is minus bj. Okay, so if I solve it, so you see here this bj square and this bj square cancel it up, then I have 5bj and minus bj, that is equal to 4bj, and this is plus 6. So this energy gap delta E is going to be how much? I can say see that this is bj square and this is minus bj. Okay, and here I forgot this is 6b, because this I am multiplying this and this and this is 6b. Okay, sorry, so this is 6b. So here we see that b is common, so b is I take common, then I say that 4j plus 6, this is the delta E. This is the energy gap for rotational Raman spectroscopy. Not rotational spectroscopy, rotational Raman spectroscopy, because here the selections rules I have used, that is delta J equal to plus minus 2. That's why I get this one. If I use plus 1, that is for rotational spectroscopy, I get something different values for here that we have discussed in rotational spectroscopy. Or we can simply put this equation and you get this. Okay, so this is that energy gaps. So why I am interested with this energy gap, because whenever you did it, we see that this energy gap we get it. Okay, so this is the energy that we given by electromagnetic radiations. Okay, after that it gained this energy and it released this amount of energy, let's say h dash, and this is the energy gap. So we have discussed for that cases we have discussed that it is gaining this amount of energy and this is releasing after this amount of energy. This is this values and this values we have discussed it. So what is that energy gap? That energy gap is we calculated, that is this amount. Okay, so I will say again, I will not do it again. Let's say for first case is that elastic collisions, there energy gap is 0, because here whatever you give you give this electromagnetic radiations h nu, then this is, let's say here rotational spectroscopy means j equal to 0, j equal to 1, j equal to 2, j equal to 3, and this energy gap, let's say this, and this is again written back to same energy. So whatever this h nu, there is no exchange of energy happened, means energy is 0 here because no exchange of energy. Okay, and the second case, two case, that is true with let's say a low frequency. This is the inelastic collisions. Here what we see that these are the energy gaps. Let's say this is j equal to 0, this is j equal to 1, this is j equal to 2, this is j equal to 3. So here what we see that, let's say they are giving that electromagnetic radiations h nu, then this energy goes here and this. So this is that low frequency because this h nu is greater than h nu dash, and this h nu is equal to h nu dash plus this amount of energy gaps plus delta E. Okay, so this delta E is equal to this amount. Okay, so now I can write here this h nu equal to h nu dash plus, that is B for j plus 6. Okay, and for other case, that is high frequency, let's say that two case, that is released with high frequency in elastic, with high frequency. In this case what you see, let's say this is j equal to 0, this is j equal to 1, j equal to 2, this is j equal to 3. So let's say this we give that electromagnetic radiations to here, and this energy, and this released, give this electromagnetic radiation, this energy, this, and this is released to this amount of energy. This is this h nu, and this is h nu dash. So here we see that this is the energy gap, and here we see that h nu is less than h nu dash. So this h nu is plus this delta E, that is equal to h nu dash. Okay, and this delta E is equal to this. Okay, so this we can say h nu plus B for j plus 6 equal to h nu dash. This is for the inelastic collisions with high frequencies. So now if I now let's say this I am doing from j equal 0 to, so this energy gap here, this energy gap is what, from j equal to 0 to j equal to 2. Okay, this is j equal to 0 to 2. Now let's consider that how that spectroscopy, that picture it will looks. That, let's say whenever you say that this is that we have discussed already, this is the relay lines, and we say that these are the inelastic collisions with high frequency, then this is the anti-stocks, and we say that this is the low frequency, let's say this is the Stokes lines. So this here that low frequency, and here the high frequency. So these are the Stokes lines, and here the anti-Stokes lines. Anti-Stokes lines. So how it that lines we will draw here. So this is that here what is say that this is the anti-Stokes lines, and these are the Stokes lines. So if I draw it in the spectrums, then how the energy gaps will look like. Okay, so now let's say this energy gaps. So we say that for this is the for Stokes lines. So this h nu equal to h nu dash plus b for j plus 6. Okay, so this h nu I want to this is the value of h nu. Okay, this is the value of h nu, because this is the relay lines, means whatever that I am giving that electromagnetic radiations that says h nu, that this energy has absorbed and same amount of h nu is released. It means that this is the h nu, or you can say that frequency or wave numbers. Okay, how I am saying this? Let's say we have that E equal to h nu, and I want to this energy, this is in the joule, this is in joule, and I in the spectroscopy you have discussed that it always we talk in centimeter inverse. Sorry, so this what I do, h nu is equal to c upon lambda. So I want this lambda means that is wave number that we talk in centimeter, so lambda, then this hc. Okay, so this I can write, this is equal to frequency. Okay, so this energy, if you divide upon hc, then that will be going to be give you this wave number. Okay, so we have that energy, that is h nu we have given, so I divide upon h c, so this h cancelled, then this upon c, and this we say that wave number. Why? Because this centimeter, this speed of light we talk, that is actually equal to speed is meter per second or centimeter per second, we can say. Then this is also again centimeter. So sorry, this frequency is second, so this cancel, and this is going to give centimeter inverse. That's why we talk it in a frequency. So this is the relay line frequencies, and this is the low frequency, and this is the high frequencies. So I want this h nu here, so I am putting this in the middle. After that, here is high frequency, here is low frequency. So I want this here, so how can I write h nu dash, then I will do here, then that is equal to h nu minus b for j plus 6. Okay, similarly, because I want this value, because this is the this value, after if you add, then we are getting anti-Stokes. If you from this, if you subtract, then we are getting the Stokes. So this value if I subtract, then these are the Stokes lines that you write here, and this is the anti-Stokes. Here also I want to put this so this value, if I add this, then I will get anti-Stokes. So this one, so here also when I can write again h nu is equal to h nu plus b for j plus 6. So here if I add, this is the h nu value, this is that this, and if I add b plus for j, means this is actually what, h nu equal to nu plus delta E, and this is h nu dash equal to h nu minus delta E. So if I here that add it to this h nu value, then this is come to the high frequency, because this frequency I am adding another frequency, that is this delta E amount of frequency. So I get that high frequency, that is called anti-stocks, and here I am subtracting the to these values about of this energy gap, then that is I am going to get stocks. Okay, so how these energy levels will be? So for that we will put, and this is, we can say that they have here the selection rule is delta J equal to plus minus 2 or 0. So here if I put here that, let's say here J, now I am putting this selection rule, that says h nu dash equal to h nu minus delta E. Here I will put for this energy gap, let's say J equal to 0 to J equal to 2, because this, you see that this is J equal to 0 to J equal to 2. So if I put this, then what you get, this h nu is itself, and here I will put B J, sorry, that is B for J plus 6, and this J here you will put that low J value. Okay, so here what you say that h nu minus B, and this is J equal 0 to J equal 2, so I will put this 0 value because we will put that low value, so that is 4 into 0 plus 6, that I will get h nu minus, this is B, this is 0 plus 6, that is equal to h nu minus 6B. So past Stokes lines will be, past anti-Stokes lines will get here. Sorry, this is the Stokes lines minus 6B, because here we are talking about the Stokes lines. Okay, so first these are the anti-Stokes, here the Stokes. So first I will get here at the difference from 6B. Okay, and the next we will go for same, that this h nu dash equal to what the values, h nu minus, and that is B J, sorry, this is 4J plus 6. So here that I will put, this is J equal to let's say 1 2 3, because selection rule is plus, because delta J is equal to plus minus 2 and 0. So here we are talking about of the Stokes and anti-Stokes, then we will use this, and when we are talking relay lines, on the time delta J equal to 0, that we will use this. So here J1 2 3, that's why, because 3 minus 1, that is actually, that should give 2 or minus 2. So here h nu dash, this is h nu minus, I will put that lower value, J refers the lower value of this transition, so here low value is 1, so I will put 4 into 1 plus 6. So this is going to give h nu minus B, this is 4 plus 6, that is going to be 10. This is going to give h nu minus 10B. So from this h nu I have to go 10. So from here I have to go to the 10. So this is already 6, then this has to be 4B. Okay, from here you say that from h nu I has to go minus 10B. This is the 10B, so this is already 6B we know, so this is 4B. Okay, similarly for another peaks if we want to get, then again we will do h nu minus B, I can write B 4J plus 6, then this we say that h nu, so B, now that 1 2 3, then I go to 2 2 4, so that the energy, that selection rule delta J has to be either plus 2 or has to be minus 2. So here that 2 to 4, whenever we are talking about of Stokes, then Stokes we will use plus 2, and whenever we are talking about of anti-Stokes, then we will use this selection rule minus 2. Okay, so we are talking about of Stokes line, so this has to be I got plus 2. So here 3 2 to 4, it means first is 0 to 2, then 1 to 3, then 2 to 4, then 3 to 5. Okay, likewise. So here I will use low value, j is low value, so 4 into 2 plus 6, that we will get h nu minus this is b, this is for 2 to 4 into 2, 8, 8 plus 6, that is 14, that is 14. So this I will get h nu minus 14b. Okay, so I have to go from h nu, I have to go to the 14. Let's say this is the 14. So this is 6, this is 4, this is 10 already, then again this is 4b. So likewise, if you go again and again, you will go only this 4, another will be here to here 18b, it means again this is 4b. So this gaps is always 4b, 4b, 4b. So past case, past time we will get 6b, after that 4b, 4b, 4b for Stokes lines. Similarly for anti-Stokes lines, so for anti-Stokes lines, for anti-Stokes lines, that is delta j has to be minus 2, and we know that this h nu days equal to h nu plus b for j plus 6, this is for anti-Stokes, so this is b for j plus 6. Okay, so now I will use, let's say I will start from 1 to 0, I will start from 0, so 0 to 2. So in that case h nu day is equal to h nu plus b. I will use this j is lower value, I will do use 4, and this is the lower value is 0 plus 6. So this is going to give h nu plus this is 0, then this is 6 only, so this is h nu plus 6b, h nu dash. Okay, so here from this I will add 6b. Okay, here from this I was subtracting 6b, 10b, 14b. Okay, so here I am adding, I will add 6b, so 1 peak here I will get. Again if I go for, let's say 0 to 1, then 1 to 3, because delta j I want minus 2. Okay, so here how I get that, here we are getting minus 2, right? Because here you see 0 to 2, so from 0 to 2 I am going, so delta j is equal to, that is final minus initial, so final is 2. Here I should get, that is minus 2. So here what you see that delta j is equal to minus 2, so yes, okay, this is minus, so here I am doing these values, so I am getting this type of values. Okay, so here that delta j equal to plus 2, that's fine, because 0, 1, 2, 3, then 3 minus 1, that is 2. Okay, and for anti-Stokes, that should I get minus 2. So here, so I am doing from 0 to 2, then higher energy level. So if you understand from this picture, let's say this is the anti-Stokes, so here what you see that we are giving this energy h nu to this, after that this is releasing to this, so this is the energy gets. So here what are doing that, from 2 to 0. Okay, this is from 2 to 0. So here the delta E each, that is initially is j equal to 2 to 0. So this is 0, So this is from 2 to I'm coming to 0. So final is j final is 0 and j initial is 2. So delta j is equal to j final minus j initial, that is 0 minus 2, that is equal to minus 2. Okay, so because here from starts you are starting, you are giving electromagnetic radiations to this excited states. After that here, so starting is 2 to 0, so final is 0, initial is 2. So if you do that, then final minus initial delta j, so final is 0 and initial was 2, so 0 minus 2, that's why you get minus 2. Okay, so delta j is actually minus 2, we should get. And if I put this values, so from here what you are getting, so from 2 to I'm going to the 0. Okay, 2 to 0. So here I will put that initial value, that is 2. Then if I put the initial value, 2 to this j replace the initial value, so 4 into 2, 8 plus 6. So today after this we will discuss more next class.